We are going to consider the first order reaction where A goes to B, in which A molecules, which are the unshaded spheres, are converted to B molecules, which are the shaded spheres. We're given the following pictures at t equals 0 seconds and t equals 100 seconds, and we're asked which picture represents the number of A and B molecules remaining at 400 seconds, and we have options A through D. So the first thing that we can do is write out the equation that describes the first order reaction, because we were told the order of reaction in our problem statement. So this is that the concentration of A equals the initial concentration of A times e to the negative kt. And for those of you that are taking calculus and feel comfortable integrating, I am going to quickly go through how we get this equation, just in case you forget on the exam and need to quickly derive it. So we know that the rate of disappearance of A, which is represented by negative dA dt, equals K, our equilibrium constant, times our concentration of A. And we know it's proportional to just our concentration of A, because it is a first order reaction. So I'm going to move this dt to this side and get negative dA equals Ka dt. And then isolate all of my a's on one side. I'm going to move this a over and transfer the negative to our side with dt. So I end up getting dA over our concentration of A equals negative K dt. And now this is just a matter of integrating both sides. So we get that ln of the concentration of A over the concentration of A naught, because in this case we're integrating from A naught to A, and in this case we're integrating from 0 to t, equals negative kt. So to eliminate this natural log, I'm going to end up getting that the concentration of A over the concentration of A naught equals e to the negative kt. And finally, that A equals A naught e to the negative kt. And if you want to memorize it, not comfortable with integrating, etc., definitely ignore this derivation, but I think it's helpful to know where this equation truly is coming from. So we have our equation for our first order reaction. So the second thing that I'm going to do is find K, because we need to know that to figure out the final concentration of A at 400 seconds, which is going to tell us which picture corresponds to the number of remaining molecules. So to find K, I'm actually going to use the first two pictures that we were given at t equals 0 seconds and t equals 100 seconds. So looking at the picture for t equals 0 seconds, I just count that we have 16 A molecules, and so I'm going to let A naught equal 16 molar. At t equals 100 seconds, I only have 8 molecules of A remaining, so I'm going to let A equal 8 molar at 100 seconds, and this will allow me to find K. So I'll write that out here. We have that A naught equals 16 molar, and then at t equals 100 seconds, our A equals 8 molar. So I can plug into this equation to get that 8 molar equals 16 molar times e to the negative kt, which is 100 seconds. So from that equation, I found that K equals 0.006931 inverse seconds. And you can find the units by knowing that negative kt right here is going to be dimensionless, and we are multiplying by seconds, so K needs to be in inverse seconds. So now that we have K, we can find the concentration of A at T equals 400 seconds. So we know that A naught is 16 molar. We have our K. We know that T equals 400 seconds, so we can solve for A. So A equals 16 molar times E to the negative K, which is 0.006931, times 400 seconds. So I get that A finally after 400 seconds equals 1 molar. So I'm looking for the picture with 1 molecule of A left. So going back to my options A through D, I can see that D only has 1 A left over. That's represented by the unshaded spheres. So my final answer is picture D represents the number of A and B molecules remaining at 400 seconds.